Hello everybody. We're still in chapter 6 and we're going to transition a little bit now. We've been talking about sequences and now we're going to move on and talk about what are series. And whenever you talk about a series, talking about sigma notation is a useful thing to do. So two things we're going to be discussing in this section. Now, two goals then. One of the goals is that you will be able to express what's called a series using sigma notation. And the second goal is that you will evaluate expressions that are written using sigma notation. Two things for you to master here. Let's go ahead and talk a little bit about definitions first though. I said we're transitioning from sequences to series, and sequences and series are related things. You at this point have learned that a sequence is just simply a list of numbers that follow a pattern or a rule. So for instance, there's a sequence right there, and it's the kind that you recognize as an arithmetic sequence with a common difference of 11 between terms. Again, the sequence is just a list of terms. Now, what a series is simply this. It's when you take the terms in a sequence and you find their sum. So this related series for this arithmetic sequence that I wrote would be the expression 5 plus 16 plus 27 plus 38 plus 49 plus 60. Okay, so a series can be described then as the sum of the terms in a sequence. And that's all it really is now. We're still going to be working with lists of terms, and they're going to follow the same patterns that we've been learning in terms of arithmetic patterns or progressions and geometric progressions. But now we're going to be adding up, finding ways of finding the sum of those terms in those sequences. All right, now in order to do that, for right now, we're going to employ what's called sigma notation. Now, sigma is simply a Greek letter, and you might use the lowercase version of sigma in some of your classes. For instance, if you take anything statistics related, you might have seen lowercase sigma written this way. All right, but uppercase sigma is this little animal right here that you've got. All right, just a big looking capital E. Now, anytime you see this capital Greek letter sigma mathematically, it means you're going to be finding a sum. You'll be adding up a bunch of things. Now, there are some other parts to the sigma notation, and one of those parts is this. If you're going to be finding a sum, you need to be able to express in some way what you are finding the sum of, and this little u sub I right there is the way of doing that. Now, we've been using the letter u to represent the terms in a sequence, correct? And so u sub I here for us is going to basically be the general formula of a sequence for which you are trying to find the sum of its terms. Okay? Now, also, sometimes you want to find the sum of every term in a sequence. So maybe if there's 12 terms, you find the sum of all 12 of them. Sometimes you just want to find the sum of the first 5 terms or the first 17 terms, or you want to find the sum of the 12th term through the 20th term. And these little numbers on top and bottom of the sigma indicate which terms in this sequence you're adding together. All right? This is what's called the lower, I'm going to call it boundary. Maybe you could just call it the beginning term for your sum. And this up here is what's called the upper boundary. And I'll talk more in detail about it, but it could be that the lower boundary, you have I equals 1, meaning you want to start at the first term, and maybe instead of n, you have 5 written, and that would indicate that you're trying to add every term from the first term to the 5th term in this sequence. Now let's see how this works when you put it into action. I'm going to do a couple examples here where we're going to write the series as a sum of terms, and hence we're going to evaluate the series. Now you see I've written some sigma notation here for the variable c, because you see the general formula for the sequence I'm going to be finding the sum of has a c in it. So those two variables have to correspond with one another. And what this is telling me is that I'm going to take this formula and I'm first going to plug in the number 1 for c, and I'm going to get a value. And then what I'm going to do is I'm going to plug in the number 2, 3, 4, all the way up to 5, and I'm going to add the results of plugging in each of those numbers. Watch. All right, you see I took this formula and I just plugged in 1 for c to begin. Next I'm going to plug in 2. And then I'll plug in 3, then I'll plug in 4, then I'll plug in everything up to 5. All right, so you can go ahead and start writing that out as such. And then all I'm going to do is I'm going to simplify all these little expressions right here so that I just have a single number or a single term there, and another single term there, and another single term there, and so forth. Now 2 times 1 plus 3 is 5, 2 times 2 plus 3 is 7, 2 times 3 plus 3 is 9, and so forth. So that will become equivalent to 5 plus 7 plus 9 plus 11 plus 13. Make sense? Now, that's actually our answer to part 1 of this problem. We have just written that series, and you can see indeed it is just find the sum of terms in a sequence. We've written that series as a sum of terms. Now, isn't that an arithmetic sequence right there, or arithmetic series that we're finding the sum of for? Because every number is 2 units apart. All right, great. Then, for part 2, where we evaluate the sum, well, that just means add 5 plus 7 plus 9 plus 11 plus 13. So that's 12, 21, 32, 45. Excellent. Let's try the next one. If you think you know what you're doing already, try it on your own and then check your work afterwards. Now notice once again that beneath the sigma, I have some variable equals a number, and the variable that's written there corresponds with the variable that's written in the general formula for the series that we're trying to find the sum of. Okay? And you're going to notice that this isn't a 1 this time. This time we're going to add everything up from when p is equal to 4 to when p equals 7. So we're going to plug in first 4, then 5, then 6, then 7 into this expression. That will give us a series as written as a sum of terms, and then we'll evaluate that series. All right, so 4 squared plus 1 plus 5 squared plus 1, and so on. Like that, and then just figure out what 4 squared plus 1 is, 5 squared plus 1, and 6 squared plus 1. And that actually is 17 plus 26 plus 37 plus 50. Now notice the difference between the terms is not constant. You added 9 the first time, then you added 11, then you added 13, so that's not an arithmetic progression that we're adding together. Just an observation I want you to make. This is the answer to part 1. And then for part 2, again, we're just going to add those values together. 17 and 26 gives you 43. Plus 37 gives you 80. 80 plus 50 is 130. All right, so hopefully you understand how to take an expression written in sigma notation and how to evaluate it ultimately. Find out what the sum of the terms with this general formula would be. What we're going to do now is we're going to kind of go backwards. I'm going to give you the terms in an arithmetic series or a geometric series or any other kind of series I feel like, honestly. And we're going to learn to write an expression for that series using sigma notation. Now, the trick when you're using sigma notation, there's 3 things that you've got to know. Let's go ahead and write the sigma, and then we can go ahead and talk about what those individual things are. We need to know a general formula that represents the terms in the series that we're adding together. And then we also need to know which term numbers it is that we're going to add together. Now, typically, what we're going to do is we're going to use the letter N whenever we write the general formula for the sequence for the terms that we're adding together, just like we've been doing earlier in the chapter. And we're going to start at N equals 1. But we don't know what the last term is. Well, I'll tell you what, in this one we do, because how many terms am I adding together? I'm adding the first, second, third, fourth, fifth, and sixth terms. So I'm adding everything from the first to the sixth term of this series. Great. So that's how you kind of get the lower limit or lower boundary and the upper boundary. Now we need to figure out what is the general formula that represents these terms here. Okay? Now, since these terms do have an arithmetic progression, we keep adding 6 each time, we can come up with that general formula quite easily. You know that in order to find the general formula for an arithmetic sequence, that you write u sub n equals u sub 1 plus n minus 1 times d. All right, so in this particular sequence then, that would end up being 12 plus n minus 1 times 6, since that's what the common difference is. Although we don't really want to write this long expression in the sigma notation, it's just not quite neat enough for us. And so I'm going to go a little bit further than we typically would whenever we write the general formula. I'm going to go ahead and distribute the 6 and then combine like terms to make this a neater looking expression. So this will be 12 plus 6n minus 6. And then that will give us 6n plus 6, all right? Because the 12 minus 6 is going to give us 6. And that is what I'm going to put here into the sigma notation. This series can be written as a sum of the terms from the first term to the sixth term of the sequence represented by the formula 6n plus 6. Makes sense? Now, if you wanted to check this, you could plug the number 1 into this formula and see that, well, 6 times 1 plus 6 is 12. You could plug the number 2 into this formula to see that 6 times 12 plus 6 is 18. This general formula does find the values of the terms of that sequence, right? Okay, let's try this with another one. But I'm going to throw in a twist. We're still going to be finding the sum of the terms in an arithmetic sequence. You can see you add 10 to negative 8 to get 2. You add 10 to 2 to get 12. And the next term would be 22 and so forth. So this would be equal, well, even if that weren't true, it'd be equal to the sum from n equals 1 to some number here. The difference this time being that I didn't make it clear which term in the sequence this number 82 is. Is it the 12th term, the 13th term, the 16th term, the 7th term? We're going to have to figure that out if we're going to be able to write out what the upper boundary is for our sum. Now I'm going to come back to that. Let's go ahead and write the general formula for the terms in this arithmetic progression. And that would be this. It would be u sub n is equal to negative 8 plus n minus 1 times 10, because that's a common difference. And then just like with the last example, I'm going to go ahead and write that in a simpler looking expression. I'll distribute that 10, make this negative 8 plus 10n minus 10, and then that becomes 10n minus 18. So we've got the majority of our sigma notation written already. The only thing that remains is for us to know which term in the sequence the 82 is. Now that's going to be pretty easy to figure out using our general formula, it turns out. Let's say that the 82 is u sub n. Well, we know that u sub n is supposed to equal to 10 minus 18, right? And so if we want to figure out what the value of n is, whenever the value of the term is 82, all we got to do is plug in 82 for u sub n into our general formula right there. So let's make this 82 is equal to 10n minus 18. And then add 18 to both sides, divide by 10, and that's going to get you n is equal to 10. So this is the 10th term in this series. And we're finding the sum from n equals 1 to 10 of the series represented by the formula 10n minus 18. There we go. Got one more for you to try here. Same idea as the last one in that we have a series in which it's not clear what the term number is for this last term. Okay, now what's different is that this is not an arithmetic series anymore, because you're not just subtracting the same thing each time to go from 10,000 to 1,000 to 100 and so forth. Maybe you can recognize pretty easily, though, because I tried to make it obvious here, that there is a common ratio. This is a geometric progression, because you could continually divide by 10 to get from here to there, and ultimately over to there. Now, with our geometric progression, then our general formula is going to look different, isn't it? Let's begin piecing together this sigma notation for this series. Sigma from n equals 1, then we want to write an expression for the general formula. And whenever we're talking about the general formula with the geometric progression, we need to know the common ratio. And remember, you find the common ratio in a geometric progression by dividing a term by its previous term. In this case, 1,000 divided by 10,000. Or you could have chosen 100 divided by 1,000 and so forth. And this will work out nicely. You could, 1,000 goes into itself once. It goes into 10,000 10 times. That becomes 1/10. That's our common ratio. And then remember that the general formula looks this way. To find the nth term, you take the first term and multiply by the common ratio, n minus 1 times. So for our series then, the first term is 10,000. So we'll put 10,000 times r to the n minus first power. That's what's going to go right here. And you could again double check this. If you were to plug in 1 for n, you would have r to, hold on. We know the value of r, don't we? So there's no reason to put that as an r. We can replace that with 1/10. And that's what I need to have right here, is a 1/10 also. See, it's a good thing I was checking my answer here. All right, if I were to plug in 1 for n, I would have 1/10 to the 0 power, which is 1. 1 times 10,000 is 10,000. If I were to plug in 2 for n, I would have 1/10 to the first power, which is 1/10, and 1/10 times 10,000 is 1,000. So this general formula does work to express the terms in that sequence. We still need to figure out what term 0.001 is. How are we going to do that? Pretty much the same way we did the previous thing. We're going to say that this is u sub n, and then we'll substitute that into our general formula right there. And we'll find out what value of n would make that true. All right, so 0.001 equals 10,000 times 1/10 to the n minus first power. Now, just to let you know here, our unknown in this equation is an exponent, isn't it? And how do we solve equations that have exponents in them, or the unknown is part of an exponent? We use logarithms, don't we? All right, so we're going to take a log of both sides of this equation. Then, since this is a logarithm of a product on the right side of the equation, we're going to separate that into the sum of two logarithms, such as this right here, the log of 10,000 times 1/10 to the n minus first power becomes the log of 10,000 plus the log of 1/10 to the n minus first power, and we'll still have the log of 0.001 on the right side, or rather the left side, excuse me. All right, now I'm going to start making this a little bit easier to look at. These numbers are quite easy because 0.001 is a power of 10, 10,000 is a power of 10, so we could actually evaluate these mentally. Think about what power of 10 would give you 0.001. Well, that would be -3. You can just type in log of 0.001 on your calculator, you get the same thing. And the log of 10,000 is the same thing. Well, 10,000 is 10 to the 4th power, so that's going to give you 4. And then let's use the power property and make that log of 1/10 to the n minus first power into n minus 1 times log of 1/10. And then we got a couple more things to do here, and we'll have the value of n. Let's go and subtract 4 from both sides, so that'll become -7. on the left side equals, and then the log of 1/10 is going to be -1. So we'll have -1 times that difference n minus 1, which for some reason this pen won't let me write. Got it. And then I'm going to divide both sides by -1 to get rid of that negative sign. And then add the 1. Turns out that this 0.001 would be the 8th term in that expression. So the upper boundary or the upper limit of our summation, okay, is going to be 8. That's using summation notation, and that's what series are. Thanks for watching, guys. I know this is was a pretty long video, but it will be very useful to you to have watched this. Again, thanks. See ya.